First value you're going to type in is the chi-square value. That's the lower bound. The upper bound is infinity, 99999. And then the final value is your degrees of freedom. And the degrees of freedom for a chi-square test is the number of categories minus 1. So how many categories are up here? 4 categories. The total never counts as a category, so 4 minus 1, so the degrees of freedom here is 3. So to get to the chi-square CDF, you're going to hit second distribution, go to chi-square CDF, it's the second one. Something's wrong. Go second distribution, whoa. Second distribution, chi-square CDF. Lower bound is whatever your chi-square value was, which is 31.15. Upper bound is infinity, degrees of freedom is 3. Hit enter and it's going to give you the p-value. Is my p-value 7.9? No. What is my p-value really? Okay, so about 0. Anytime you've got zeros within the first 4 decimal places, you can pretty much say that your p-value, so your p-value is 0. Compare that to your alpha level of 0.05, and it's less than, so what are you going to do? Tyler, what are you going to do? Reject the null. Very good. Now, reject the null. If you just write reject the null, though, you're not going to get any credit. What does that mean? What did we decide? So let's go to our null. The null says the distribution of birthdays in the NHL is uniform. We are rejecting that. So it isn't. Meaning the birthdays, the distribution of birthdays in the NHL is not uniformly distributed. So the conclusion here, the conclusion we're going to make, the distribution of birthdays in the NHL is not uniformly distributed. That is our conclusion here that we're going to make. We reject the null. That means we are deciding that distribution of NHL birthdays is not uniform. Now, the next question here says, does that data suggest that some quarters are more likely than others? Well, the data may suggest it. Don't you think that the data suggests it? But does the test, does our test tell us anything like that? No. You need to understand that a chi-square test, it's not going to tell you which quarter has more. It only tells you that it's not like what we observed is different from or the same as what we expect. So a chi-square test can't tell us if some quarters are more likely than others. The data suggests it, but the chi-square test doesn't tell us that. It only tells us if it's different from or the same as a given distribution. So this is something to think about in your projects, because as soon as we do more of these, and I know your project proposals are due next Tuesday, you might be thinking, oh, I like that chi-square test. That's pretty simple. Okay, there's less to write in the calculations. It's pretty easy. But if you're trying to prove that something is better than, worse than, the same as something else, then the chi-square test won't do that. The chi-square test only says if the observed and expected differ from each other. So, and there's actually 2 other types of chi-square test. There's a test for homogeneity and a test for independence. So we'll talk about those too. They might, if that's all you're trying to decide is if something fits something or not, then might be a good idea for a project. All right, so now we're just going to walk through another chi-square test back here. We're going to write all the steps down. But another common application of a chi-square goodness of fit test is to see if a distribution follows of data follows a theoretical probability distribution. So, for example, is the outcome of a roll of a six-sided die uniformly distributed? In other words, if I roll a regular die with 1 through 6 1,000 times, I should get the same exact number of 1s, 2s, 3s, 4s, 5s, 6s, right? Because it's equally likely to end up with 1 through 6. Okay, is the number of hits in 5 at-bats binomially distributed? Like you could get 2 hits out of 5, 3 hits out of 5, 4 hits out of 5. We had the binomial probabilities where what's the probability that I get exactly 2 out of 5, exactly 3 out of 5? And or is the distribution of human heights normally distributed? So we're going to deal with normal distribution in just this example. So farmers in Idaho believe that the weights of potatoes are approximately normally distributed with a mean of 7 ounces and a standard deviation of 1 ounce. I'm just going to draw myself my normal picture just so we can visualize it. So my mean is 7 ounces, my standard deviation is 1, so this would be 8, 9, and 10 ounces, 6, 5, and 4 ounces. So in other words, farmers believe that most potatoes are around the same size, with a few big and a few small ones. Okay, that makes sense, doesn't it? You know, potatoes, most of them grow about within, probably 6 to 8, and then the rest of them are smaller or bigger. And you don't usually have a potato like 27-ounce potato. That's very, very unusual. All right, so we need to see if these are the categories that they put them in. So less than 6, so we put them in these categories. Less than 6 is over here, so that's this category. Category 1 is over here. Between 6 and 7, this is category 2, number 2. This is number 3, and this is number 4. Okay, and the reason I'm doing this is because we have these are called the observed counts here, observed counts right there. Our data is what we observed. So in each of these categories, that's what we observed out of 1,000. We want to figure out, well, what would we expect the percentage in each of these categories to be if this were a normal distribution? So we better add up to 100%. And then based on that, what would be the expected counts? And our expected counts should add up to our observed counts. Okay, so in a normal distribution, I'm going to start in these middle 2 sections because I know that 68% of data is found within 1 standard deviation above and below the mean. So that means 34 in each of these. So these 2 categories get 34% in each one, and that's just based on the normal distribution. And these outside ones, well, they have, let's see, 68% in the middle, so these have 32% to share, so 16% in each. And that's just based on the values from the normal distribution. So now, the way I calculate the expected counts is I take my total, 1,000, and I take it times each of these percent. So 16% of 1,000, so 0.16 times 1,000. And that's going to give me 160. So that's 160 there, which means that this last one's also 160. And 34% of 1,000 is 340. So these are my expected counts, my E's. These are my observed counts, my O's. So does there appear to be a difference between the 2? Yes, there does appear to be a difference. So we're going to do a chi-square test. So we're going to do step 1 here. We're going to write our at first glance paragraph, very similar to the one on the last page. So our step 1, first glance it appears the potato weights are not uniformly distributed since my observed and expected counts are different. This could be due to sampling variability. So we're going to do a chi-square goodness of fit test at alpha level 0.5. Step 2, name my null and my alternative hypothesis. So, the null is that potato weights are uniformly distributed. Or, not, did I say uniformly? I shouldn't have. I meant normally if I didn't. Potato weights are normally distributed. And the alternative hypothesis is that potato weights are not normally distributed.
So in step 1, should the weights are not normally distributed?
Yep, it should say normally. I knew I was doing something wrong, so it should say normally distributed in here. First glance, it appears the potato weights are not uniformly distributed since my observed and expected counts are different. Thank you very much. Okay, so the null is potato weights are normally distributed, and the alternative potato weights are not normally distributed. You could just say they're not in the alternative. Okay, step 3, we're going to check our conditions. And if you've already got your table made, the conditions are pretty easy to check. It's the same as other conditions. The only thing is the large sample size. You have to remember that all the expected values have to be greater than 5. So check the conditions. It is stated as random sample. We're going to assume that 1,000 potatoes is less than 10% of all potatoes. And third, all expected counts are greater than 5, greater than or equal to 5. And you must provide the table. Must provide table. And we've already done that. We don't have to provide it again. We have already provided it here. This proves that our expected counts are all greater than 5. All right, now we need to do our calculations. So our chi-square value, step 4, our chi-square value needs to be calculated. The sum of all of our observed minus the expected squared all over the expected. You can actually use your calculator to do this test. You can use your calculator to do this test as long as you write down this formula, and then it'll actually calculate the chi-squared for you. It'll calculate your p-value for you. So in order to be able to use this test on your calculator, you have to go to your lists and you have to enter your data in the lists. So you would enter your observed in list 1 or whatever list you have, and then your expected. So you still have to do the calculation of the expected here. Okay, so you enter them in a list, and then you're going to go to stat tests, and if you go down, you'll find a Chi Square GOF test. And you can tell it that where your observed and expected lists are. Mine happen to be list 2 and list 3. And then my degrees of freedom. What's my degrees of freedom here? 3. Yep, categories minus. And then I'm going to calculate it. And it actually tells me my chi-square value is 41.624. My p-value is 4.8 times 10 to the negative 9th. So my p-value is approximately 0. All right, and then I have my degrees of freedom. I need to write my degrees of freedom as 3, and then don't worry about this part down here. Okay, don't worry about that. So what would we do? P-value is 0. Our alpha was 0.05. It's less than, what are we going to do here? Reject or fail to reject? Reject the null, and we're going to conclude that potato weights are not normally distributed.